Hello, my name is Gonzalo Abad, and in this video tutorial we are going to see an analytical model of doubly fed induction generator for online simulation purposes. All the information related to this topic can be found on these books: Doubly fed induction machine modeling and control for wind energy generation, the English and Chinese version, and Power Electronics for renewable energy systems, transportation and industry applications. Both books have been edited by Wiley. And more specifically, the topic that we are going to treat on this tutorial can be found specifically in chapter 4 of this book and at the beginning of chapter 10 of this book. So we will continue from the tutorial from the simulating program that we developed in previous tutorial number 8. So let's open the simulating program. And the idea is simple. Let's wait. Yes, here it is, our program. The idea is simple. What we are going to do is just develop a doubly fed induction generator model, which is of our own, based on the analytical equations and the analytical model of this machine. We are going to substitute this machine model provided by the SimPower System library, and we are going to develop our own generator model. So first of all, let's do a little bit of theory about this generator model. So let's go to the PowerPoint program. Here it is. Our starting point is going to be the doubly fed induction machine model in alpha beta, or a stationary reference frame representation, which can be seen here. Here we have the alpha component, and here we have the beta component, equivalent electrical circuit. This is the analytical model from which we are going to start everything. You know that this can be modeled mathematically by a set of two equations, one for the stator and one for the rotor voltages. And this can be made in a in a space vector representation, which has two components, or yes, as we have said, alpha and beta for each voltage of the stator and of the rotor. So here it is the stator voltage equivalent circuit represented by these equations. Here we have alpha and beta stator voltages. Here we have alpha and beta stator currents. And here we have the stator resistance, which is given by this equivalent voltage drop. And here we have the stator flux equivalent voltage. And on the other hand, we have the rotor voltage. Here it is the rotor voltage for the alpha component, and here we have the the beta rotor voltage for the beta component. Here it is the alpha voltage. Here we have the beta rotor voltage, these two terms. Here we have the rotor resistance due to the copper losses. Here we have these two terms. Then we have two coupling terms due to the speed of the machine and due to the rotor flux, which are these two terms, and which are these two terms. And finally we have the rotor flux equivalent voltage, which is these two terms. Then for the model, we can also have two flux equation, in a space vector representation as well, that we have that can be decomposed in another two alpha beta for the stator flux and alpha beta for the components for the rotor flux. So here is the stator flux, which is given by this flux, and this is the equation. This is the leakage, stator leakage inductance. This is for the alpha, and for the beta equivalent circuit, this is a magnetizing equivalent inductance for both circuits, alpha and beta. And here we have the rotor leakage inductance for both equivalent circuits in alpha beta. And here we have the equivalent expressions. So this is our model. This is going to be our starting point in order to develop the analytical model that we are speaking about, to substitute it in Simulink. Yes, here we have another equation, which is the torque provided by the generator at the shaft while it is rotating. And here you can see that can be calculated by means of these two coupling terms, by means of these electromotive forces induced at the rotor, because due to the fact that this is losses, these elements do not create power, power or torque, and neither these two elements create power, but they are losses, just the opposite. The only element in which the power is created is in here. So if we multiply this element, this voltage, which is given by this expression, multiplied by the current, plus this voltage multiplied by the current, and then we divide by the speed, that will be the power divided by the speed, we achieve the torque, which is given by this simple expression. Okay, so once we have the model, our starting point model, by taking these equations, these 2, 4, 6, 8 equations, we can manipulate them, we can take them and obtain equivalent expressions, and the idea is to represent these equations in a state space representations, in which the state space variables that we have chosen are stator flux and rotor fluxes. We could use any other, there are many other possibilities, there are many other combinations by using stator or rotor currents, but due to the fact that this state space representation is quite simple, the equations that we obtain are quite short, are quite simple, we are going to use just this one. So by developing for each space vector the alpha beta components, we can obtain this state space representation. Okay, so by using this state space representation, which is the analytical model, which could be one of the possible analytical models of the Doubly fifth induction generator, from here, from these equations, we are going to derive the Simulink program that we are going to implement in our system, in our Simulink program. Okay, so let's go to implement the program. Sorry, yes. So let's go to the Simulink block. So what we are going to do is just develop one equivalent model for this generator, and we are going to put it in parallel to this element, to this Simulink power system block which is already developed. So we will need one block. Let's use this one for instance, and let's copy it there, and this is going to be our model. Let's give it that name, for instance. Let's go inside, and we are not going to need many of those elements, so let's remove what we don't really need. Probably yes, okay. Let's left what we could need. Okay. And here we have functions, and we will need the functions. So the idea here, we can implement this space representation in many different ways. We could do in many equivalent manners, but what we will first do is just perform this mathematical expression, this product of two matrices, and then the addition of this vector. Once we have this result, what we are going to do is just integrate in order to obtain the state space equation, the fluxes. Okay? So we will do it in this way. We will need, let's have a look, 4 entrances, 4 inputs, then 4 space vectors, 4 elements for the space vector, and then here we have the element, the speed, which gives nonlinearity to this state space representation. This system is nonlinear due to these elements which could change. Sorry. These elements give us the nonlinearity. This should be an input as well. And nothing else, I think. So we will need 4 inputs, 5 and 9 inputs, if I'm not wrong. So let's do this bigger. And we will need, let's eliminate what we don't really need. Let's leave it cleaner. We will need 4 functions, 1 for each flux that we want to calculate, that we want to estimate its state. That will be the inputs. Sorry. 2, 3, and 4. Then this will be the fluxes, and then we will need to integrate in order to obtain, well, this will be the derivative of the fluxes, and we will need to integrate in order to obtain the actual fluxes. So let's use, for instance, one integrator that we could take from here. I don't remember where we can find one. Yes, for instance here. Let's take it. We don't really need saturation. This is for the PA controller. We are doing something totally different, so we don't need to limit the output. And here at sample time, we are going to use the sample time of the simulating, of the whole simulating program, because this is not control, this is model, and the model should be faster than the control. TS, that should be, let's open the initialization program. TS, it's here, is 50 times smaller than the switching frequency. That in our case It's a value. Sorry. It's a value of 5 microseconds. Okay, so we have here this. We have here this. We have here this. And we have here this. Then we need another multiplexers of 4 inputs. Let's do a smaller, this element. Okay, and let's connect it there. And like there. Okay, so here as inputs we will need, okay, these are the fluxes, alpha, beta for the stator, alpha and beta for the rotor. So here we have multiplexed or the fluxes. Then here we will need the stator voltage. Then we also need the rotor voltage, and we will use ABC input voltages. So therefore we will need from ABC to DQ this transformation in order to, okay, this is alpha beta, sorry, this will be like this for the rotor, and this will be alpha beta. Alpha, yes, beta, and the same inside. It is the same transformation. This is the Clark transformation, but the names in this could be different. Okay, so here we have multiplexed 2, here we have multiplexed 2 inputs, then we have the speed, and finally we have okay, so we have here too many, 2, 3, 4. With 4 is enough, I think. Let's see if, sorry, this is not correct, but there will be 2 as well. Then we have the speed that will come from our model. Let's put like here, let's call it in that way in order to distinguish from our model and the simulating program. With this term we will say that these are variables, in this case speed, of our own analytical model. And here we do this. Okay, and here we will need another equation, another function, in order to calculate the torque. Let's connect it there. And then we will need go to, not really yet, okay. So that will be the torque. We will later introduce, put here the equation. And then here we need to use the mechanical equations, which is very simple, but we will need this element. This is the torque. Let's rotate, Control R, and let's take everything to the left, to that way. Here we will need the load torque. The load torque that is coming from outside in this application is going to be the wind turbine torque, the torque provided by the 3 blades. Therefore, we will need another input. This is the load torque. Let's call it in that way, in a more generic way. And let's take it down. So this is torque. Then we will need to divide by the inertia. We won't use in the mechanical system of this equivalent analytical model, we won't use damping, something like here. We will use only inertia. So let's do it in that way, in order to be simple, in order to don't go to too many details, but you could do it very simply. So let's put it here 0, the damping ratio of the mechanical system of the model of the shaft, and we will only use the inertia. Here it is. So once we have this, then we need another integrator. That will be acceleration. This will be acceleration, and here once we integrate it, we have rotational speed in mechanical radians per second. Yes, this is omega m, so we need to multiply it by the pole pairs. And this will be this omega. So now we need to go to, let's find it here, for instance, here. We copy it from there, and that will be, if I'm not wrong, omega m. Right. Let's copy the name from there, and let's put it there. Sorry. Okay. Let's take a little bit more space there. We have omega, we have the speed in electrical radians, but we will need also the angle theta. So we need to integrate again, and that will be theta m in order to do the transformations from different reference frames. The first one that we need to do is for the rotor voltage, because the whole state space equations of the analytical model of this machine is going to be in alpha beta, in a stationary reference frame, like in here, like the stator voltage. So we need to transform this rotor voltage, and we will need one transformation. For instance, this one. Let's copy it from here and put it there. So we need to add, this is omega r, theta r. So we need to add, yes, this is a little bit tricky, but it will work. This is -1. Let's do some space here. Let's put it there. And then we need an angle theta m. So we need this go to. Let's rotate it. No. We need space. And this will be theta m. and this will be alpha beta, and inside as well alpha beta. Let's think about it. Theta the Q we are adding, okay, it's correct. A little bit tricky, but it will work. And just keep in mind that this equation that we are applying is the typical, a simple mechanical equations that in our books, for instance, in chapter 4, if we go to page 10, if I'm not wrong, yes, it's here. This is the mechanical equation, the mechanical model of the shaft that we are applying, just one inertia. So this equation is just one, that one here. Then we multiplied the speed, which is in mechanical radians per second, by the pole pairs in order to obtain speed in electrical radians per second, and then we integrate in order to calculate the angle theta for the transformations. Okay, so once we have this, I think that we have almost everything. We don't need this output, we don't need this. This is the torque, so I would like to make some more space. Let's do this smaller. Let's take it to there. Let's take it to there. This will be there. Let's rotate it. Let's do it smaller. And let's do this like here. So now we can do it bigger and we can make some more space. And with this, we have everything quite to the left. Okay, so now we need to implement these 4 equations for the fluxes and this torque equation. So we will need to keep in mind this element. Let's do this smaller. Let's do it in this way. So first we need to obtain the first derivative of the stator alpha component flux. So we need to implement this equation, this first row multiplied by this vector plus this element. So let's go carefully because here it is quite easy to do it wrongly. So we need to multiply. Let's call to this element A11, A12, A13. So multiply by the first one. No, not the first one, but the flux. The first flux is going to be 2, 4, 5, 6. So this is going to be 6. Then we have something very equivalent, plus A13, which is this element multiplied by this element. If this is 6, this is going to be 7, 8. This is 8. And then we need to add to this element, which is this one, the first component, plus U1. Okay, so this is the first equation. Then later we will define these elements, A11, A13, and so on. Let's do it first here. So let's copy it there. So in this case, if this was U6, now we need U7 multiplied by A22. Then we have A24 multiplied by, that will be 9 input, and the second stator voltage, the beta component, will be U2. Okay, so let's do the same, but let's copy again there. With the rotor flux, that will be A31 multiplied by U6. Yes, U33 multiplied by U8, and in this case we need to add another component that will be U9 and this will be minus the speed 2, 4, 5, U5. Okay, negative, okay, and the input will be U3 on the rotor voltage alpha component. This will be more similar to the previous one, so let's copy it from here, from there. So that will be U42, U7. U4, let's do first this, U44, U9, and then this term will be positive, we are with this term, and this will be 5, in this case will be 8, and therefore the input rotor voltage will be beta, therefore it's 4. Okay, so I think that everything is there. So the only part which is missing is the torque. So for the torque we need another equation here. We need another equation that can be taken from the book, from chapter 4, if I'm not wrong, and that was page 6 or even, yes, here we have several equivalent torque equations, and the one that we are going to need or we can use is, because we are using fluxes, stator and rotor fluxes only, in order to calculate the torque, we will use this equivalent expression. So let's go. So here we have 1.5 multiplied by P multiplied by Lm, if I'm not wrong, divided by sigma multiplied by Ls by ampere. Sigma Ls Lr. Let's check. Okay, and here we have a product, the product, which is in this case where we are. So therefore we need to multiply everything by U2 multiply by U3. That will be beta stator alpha rotor, always cross, and then minus U1 alpha stator multiplied by U4 beta rotor. Okay, so that will be the torque in this equation. Yes, I think it's correct. And then what else do we need? What else do we need? Okay, if this is going to be one model substituting or equivalent to this one, we need rotor currents and we need stator currents. Stator currents must be calculated from the stator fluxes and rotor fluxes, which are here. So therefore we need another equation that should be taken from the book, I think in chapter 10, in page 10 as well, if I'm not wrong, yes. Directly here we can use one equivalent model expression that gives us the stator currents in function of these stator and rotor fluxes in alpha beta components or a stationary reference frame. So let's do some space. Yes, we will need another function here. This is the input. So we have to implement this. Let's put it there. 1 over sigma over ls, all this multiplied by u1, which is the alpha component of the stator flux, minus Lm divided by sigma divided by ls divided by r. And all this must be multiplied by u3, which is the alpha component of the rotor flux. We could do it something bigger. I think it's correct. Sigma ls u1 minus sigma ls u3. Yes. And the beta component of the stator current, is going to be something very equivalent, but in this case we need to use the beta components, which is u2, and this is minus as well, the beta rotor component, which is u4. This is a stator currents. These are stator currents in alpha beta. Therefore we need to transform, for instance, to ABC. Therefore we need another transformation, which could be this one, where it is, where we are here. We need another multiplexer, probably here there's a smaller one. Okay, this is going to be alpha beta, let's call it properly, which is the equivalent transformation. And here we have the multiplexer 2 into 1. Here it is, and here it is. And therefore this is going to be stator currents in alpha beta in ABC components. So let's call it with another go to IS, like this. And let's connect it there. So this is our models, the stator currents in ABC. So let's do the same. Yes. So let's do the same with the rotor currents. we need to calculate again. Sorry, whoopa. I don't know what I did. Okay. We need to do something equivalent with the rotor currents. This will be a little bit more complicated. We need to reach the... Okay, let's go step by step. Let's first calculate the rotor currents. In order to do that, we need another equation, which is in, if I'm not wrong, in chapter 7. Yes, chapter 7, page 38. Yes, here we have the expression, one expression that gives us rotor currents in function of stator flux and rotor flux, which is very equivalent, very similar to the previous one. If you realize, here it is the difference, and then we need to cross the terms. Let's put it there. Yes, I think that we will have space enough. We will move to here. So let's copy one function to there. Let's move it down there. Let's move it down there. Let's connect it properly. So in here we have sigma divided by LR. And here we have, let's think, rotor current is going to be positive for the rotor current. And sigma LS. Okay, so here we have just changing. U3 sigma IR. U3 is sigma LS, yes. Sigma LR, and negative is going to be a stator flux. Yes, I think it's correct. And something similar with the beta component, which in this case is going to be, this one is going to be U4, and this one is going to be U2, with the beta components like that. Yes, I think it's correct. Okay, these are alpha beta components. These are alpha beta components. So I need more space. Let's do it. By this way. Okay, so now we have to pass to dq. In this case, this is going to be dq. And this is dq. Sorry. And then, sorry. We will need again this transformation, which again is, these are just names, dq, and this is dq. This is just one transformation from two phases to three phases. So let's connect the output there. Let's connect it there. And then we need also another multiplexor, connect it there. And this is wrong. Obviously this is wrong. This is minus. Let's do it smaller. Sorry. This is theta m again. we don't have too much space, and obviously this should be 1. There shouldn't be any multiplier. Sorry about this. I think that now is correct. This is rotor current. Yes, alpha beta. We need to subtract, therefore we need the minus, and this is dq and abc. Yes, I think that everything is correct. Okay, so now we need a stator voltage through here. For instance, just keep in mind that was coming from this measurement. Now we don't need the zero order hole again, because this is not control. This is not going to be implemented in theory in a microprocessor or digital signal processor. In this case we have the model, therefore we don't want to have any delay or any quantification. And for the rotor voltage, okay, this is the load which comes through there, and for the rotor voltage we need to create this measurement that we don't have already. So it should be here, voltage measurement, yes, face to ground, sorry, use a label VVR. Okay, so it's there. Yes, it should be there. So this is the rotor voltage. Be careful, because these are actual rotor voltages, and here with this transformer, this model of the machine is referred to the stator, and this is real values where we are taking the reference. Okay, so we need to refer to the stator. Let's take this. Therefore we need to multiply by U, sorry, let's do it smaller. This is 1, and for the rotor currents, if we want to compare them with the model, we will need to do the same. So we need to multiply the rotor currents of our own model by U in order to be possible to be compared with them. Let's do some space. We have problems. This is quite complex and big, so we need some space. Let's do it smaller as much as we can. Okay, and let's put there. Can be watch everything. I hope we can see everything. Let's do some more space. Okay, so I think that the model is already created. So once we have the model, let's compare it, how it works, if it's similar or equivalent to the Simulink SimPower library model. So let's go to the monitoring block, and let's use, for instance, another scope. in which we could compare three variables, let's say. Let's do the layout like there. Okay, let's compare the torques. Let's call it in this way, torques. Let's use also, let's compare stator currents, and let's compare as well rotor currents, IR. If everything is, if all those variables are equivalent, the model will be the same. If everything goes well, we will see how it is true. So let's find where it was the torque. Let's take, for instance, these elements, copy them and paste there. This is our model comparison. So that will be, for instance, the real torque, and then we will compare it with the torque calculated by our own analytical model. We haven't created this torque, but it's there. Let's use one torque from there, and this will be our own torque. And then let's compare these two currents. So let's go there again. It's there, copy there. This is going to be stator current, and this is going to be our model stator current. Okay, and the same for the rotor. This is IR, okay, and this is going to be IR. Okay, so we will compare them. Okay, once we have this, what else? Oh, obviously these are missing as well, these variables. A11, A13, and so on. Okay, so let's go again to here, and let's go to the initialization program. Let's add some more lines. Okay, so A11 is going to be, minus RS divided by sigma divided by LS. A13 is going to be something similar, but not the same. A13 is going to be plus RS multiplied by LM divided by sigma divided by LS and divided by L. Okay, A22 is going to be equal to A11. Sorry, A24 is going to be equal to A13. Okay, that was for the stator flux, and A31 is going to be equal to something very similar to this one, no? The same structure, very similar structure, but in this case, the rotor resistance is there. and then 832, 833, which is this element very similar again to this one. There is big symmetry in this machine. R sigma R. Okay, this is A4 2 is going to be equal to A31, and finally A44 is going to be equal to A33. You can see here that with this state space representation we can use any control theory from the classic automatic or control theory that we want. Okay, so let's initialize the program. Okay, it seems that everything is correct. We don't need this anymore. So let's simulate the program and see what happens. That will take some seconds because we have the accelerator. So let's wait. Okay, so it seems that we have been lucky and there was no error, so it's working. Let's use the scopes, the grid side converter and the rotor side converter. Let's have a look of the model comparison, and it seems that everything is okay, but let's wait until the simulation finish. Just remember that this is the simulating program where we left in video tutorial 8. We are working with this wind speed and we are performing a symmetrical voltage dip at the stator. That will happen, if I'm not wrong, at second 3. And the simulation will finish at 4.3. So the simulation is running, and here we see how at the beginning we have at the grid side converter a big overshoot at the stator at the DC bus voltage. Now there is control of it. It is working, it seems, the current loops and so on. And here we can see the model comparison. We are comparing torque, both torques of the simulating program, both the simulating model and our own model, the stator currents in ABC and the rotor currents in ABC. So here we can see that all these variables that we are comparing are superposed. Therefore, it seems that both models that are equivalent or are the same. The one that is provided by Simulink, by the SimPower library, and the one that we have been developing. This one in here. Okay. So let's wait until the program is finished so we can see the voltage dip, the asymmetrical voltage dip, and we will see how in all the conditions now it seems that it has occurred. Here it is, the asymmetrical voltage dip. It is working, the wind turbine is working with the imbalance and with the difficulties created by this voltage dip or this perturbation, but it seems, or at least it should, that both models are performing in an equivalent manner. We see how the torque is oscillating due to the voltage dip. The stator currents are deteriorated and the rotor currents are also deteriorated, but from the model point of view, both models are working equivalently. So let's wait a little bit more. It's needing some time because we have in this computer many programs working. Let's close some of them. So maybe we help to the memory of the computer. But now we will finish. Now we will have the voltage recovery, if I'm not wrong, a second 4.1 or 2, no, 4.2. Let's be patient. Now here we have the voltage recovery, which is another perturbation for the system. It can be understood as another perturbation, but the system is still working with its transient. And finally, the simulation has finished. So let's focus on the model comparisons. And here we can see how both models are working in the same condition. Let's focus, for instance, at this time instant. I don't know. Let's take, for instance, here. And here we see how all the variables are quite well matching. Torques, stator currents, which are there, and rotor currents. Okay, we can do a zoom bigger. There it is, the difference. There is a short difference at the torque. And here we see as well, and the stator currents, they are not exactly the same, but very, very near. And for the rotor currents as well, we have very big similarity. Okay, so that was all. I hope it was interesting and useful for you. Thank you for your attention. Thank you.